Hey guys, so this is a brief review video about dimensions and units, and then we'll also talk about some physical constants, right? And so here I have the four base dimensions that we're going to be working with. And there are three more. Um, and notice these are set up. Know that these are set up by the System of International Units (SI) units. Um, and or in English, we generally say the International System of Units, but it's the SI is from the French term for it, which is like Système International. So, um, so we call them SI units, and so they recognize these base dimensions, and the ones we're going to be dealing with, the dimensions of time, which I'm going to put dimensions in brackets, right? So time, length, current I, and mass m, right? And time is going to be measured in seconds. Length is going to be measured in meters. Current is going to be measured in amperes. And mass is going to be measured in kilograms. So we can have other dimensions, though, as well, and other units, right? And so, for example, right, we can have force, right? Right? The dimensions of force, which are, right, well, we know acceleration, right? If we have the dimensions of acceleration, it's measured in meters per second squared, right? It's length per time squared, right? And so since force, right, is mass times acceleration, right? We know this is mass times length, or sorry, mass times length over second squared or time squared, right? And so we can measure this. Well, we measure force in newtons, right? But a newton, and I'll put this in a different color, a newton is equal to a kilogram times meters per second squared, right? So same thing with energy, right? Energy, I'll do one more after energy, is force times distance, right? So it's going to be mass times length squared over time squared, right? Which would mean 1 joule, which is the unit of energy. 1 joule is equal to a kilogram times meters squared per second squared, right? Hopefully using this you can like figure out what the dimensions of momentum are, what units we'd measured momentum in, right? And this is a Newton times meter, right? One last one that we'll do for right now, which is charge, Q. I'll do it in this color just because it's getting a little close to this stuff. So Q, right? Charge is the amount of current that goes by through amount of time. Really, it's probably better to think current is the amount of charge that goes through a certain amount of time. But uh, the System of International Units determines that current is actually the base unit, right? Which it's arbitrary, but so this is, right, the units of current times the units of time, right? It really makes more sense to think of current as charge over time. But, all right, and so we measure this. This is in coulombs. 1 coulomb is 1 ampere times second, or an ampere is a coulomb, is coulombs per second. Okay, so I'm gonna erase this right now. Hopefully you've got that down if you didn't already know this, but this should make sense. Um, just a few things. Um, so rules for when we're working with this, right? So the first thing is when we multiply and divide quantities, we multiply and divide their units, right? So, for example, we have, right, let's say we have force times, I don't know, force times length, or force times velocity. There we go. Force times velocity, right? Well, this is in newtons, this is in meters per second, so this would be measured in, right, newtons times meters per second, which it would be a joule per second, right, which we actually call a watt, right? So that should hopefully make sense. Just when you multiply and divide their units, right? Generally, when we raise something to a power, we raise something only to a dimensionless power. So then we also have derivatives, right? And so I'll just show you with one example. If I have dx by dt, where x is a length, it's measured in meters, right? Right? Well, dx, it's just a small change in length. That's still measured in meters, right? Dx, it has the units of x. Same thing, dt, it's the unit of length, or dimension of length, unit of meters. Dimension of length, units of meters, right? And length over time, right? The units of dt are in seconds still, right? So this is sorry, it's not equal, just it's a meter per second, right? Which is the units of velocity. Same thing if I have an integral, right, of v dt, right? dt, the integral sign doesn't have any units. This is measured in seconds. This is in meters per second, right? Which would mean, because this integral, right, it's the antiderivative of velocity is position or displacement, and this is, right, this is measured in meters, right, where it has the units of length. So again, this is just going by quick. The other thing is usually when we have something in the exponent or something inside a trigonometric quantity, it's going to have no dimensions. And sines and cosines themselves have no dimensions as well. And that would kind of make sense. Sine and cosines are ratios, right? They're a ratio of one side to another side, right? Which is one length to another length, right? Which would end up being dimensionless. The one unit, there is a unit though, it's called a radian, and we've talked about radians. And radians, right, what are the dimensions of radians? It actually does not have dimensions. Radians are dimensionless. And the reason, and it's not, right, there's still a unit, and you can have a unit without a dimension. But the reason is, if we think about, we define a radian, theta, is the ratio, right, of, really, I should have said this is the dimension of theta, right? There are none. It's measured in radians, right? And just because, and the units are still important, it's just it does not have a dimension. And the reason is because this is s over r, right? S equals r theta. So theta is equal to s over r, which, so we've got the units of, all right, so this means we've got the units of length, right? Arc length over the units of length, or dimensions of length over dimension of length. Hey, these cancel out. Theta is a dimensionless quantity, but it still has a unit, right? And just like we'll talk about angular velocity, or right, which is going to be measured in radians per second, its dimension is just 1 over second, right? Hopefully that makes sense. You can look up, if you don't know why angles are still dimensionless, you can just look up why a radian's dimensionless. You can look up with units on Khan Academy. It's not super hard. I'm really hoping you are familiar with this. I don't think I'll need to put any links in the video. There's just one other thing that I wanted to talk about. Oh, actually first, if we have with statistics, right? A standard deviation in a quantity, right? The standard deviation of x is going to have units of x, and you can prove that with our formulas. Same thing, expectation values, right? Expectation values, like the expectation value of x. I have the expectation value of x. The dimensions of this will just be the same as the dimensions of x, right? So the expectation value of like momentum would have the units and dimensions of momentum. Probability, however, probability is also dimensionless. Hopefully you can see why probability is dimensionless, right? Because it's a ratio, right? It's the amount, right? Like say we have a certain number we have 10 apples and 3 of them are red, right? Well, the probability that an apple picked at random, right, would be 0.3, right, or 30% if we picked it at random and it was red. And because that's 3 apples that are red over 10 apples, right, the units of apples cancel out, right? The dimensions, it's dimensionless. It's a ratio, just like a trig ratio. So the last thing are constants. And we've got some constants that we're going to be dealing with. Namely, we've got 3 that I really want to focus on. We'll talk about the others later. But we have Planck's constant, the reduced Planck's constant, and the speed of light c. And these are constants. They have a certain value, and they also have units, right? And so Planck's constant is 6.26 or 6.626, sorry. 6.626 times 10 to the negative 34th. And the units of this are going to be in joule seconds, right? Which is a kilogram times meters squared per second. Reduced Planck's constant is Planck's constant h divided by 2 pi. And this is equal to, let me just double check that. We've got the value, we've got, sorry, I didn't have this pulled up before. Okay. H divided by 2 pi is 1.055 is approximate times 10 to the negative 34th. Still joule times seconds, right? Because 2 pi is a constant, right? Right? And the speed of light, c, is about 3 times 10 to the 8th meters per second. So notice these constants, right, have units as well. So if we multiply them into an equation, we'll have to multiply by their units. Just wanted to introduce you to those so you see them. Okay, awesome. I will see you in the next video. Again, hopefully this is a review. If it's not, just look up some of the information. I may put a link in the description just to help you with this. Okay, I'll see you in the next video.